That's right.
All right, so heat capacity and calorimetry. I touched on this a little bit yesterday when we were talking about that sample with aluminum and the water. They had some values in there for heat capacity. We didn't really talk about it specifically, but when we're talking about trying to calculate heat, which is always defined as Q, this lowercase q, we need to look at the mass of the material, the specific heat value, which is individualized based on what substance it is. So they have to give you that, or they have to give you the other stuff, and you're solving for that. And that varies again by what substance it is, and the change in temperature. So how much the temperature changed over that time period. And yesterday when we were talking about the aluminum, we were talking about putting 85-degree aluminum in 25-degree water and how that would equalize somewhere above 25 degrees and below 85. Okay. So when we look at that, we're looking at, again, this quantity C, which is the amount of energy needed to raise the temperature of 1 gram of the stuff by 1 degree Celsius. Water has a very high specific heat. That's why it takes water so much longer to heat up and cool down versus like a metal. Okay. You take a piece of aluminum foil out of the oven that's been in there, at 400 degrees, okay? And within a couple minutes, you can touch that comfortably and not get burned. You do that with the same quantity mass of water, okay? And you're going to burn yourself because the water will retain that heat much longer, okay? So, definition then of heat is a form of energy that flows between two samples. We talked yesterday about the 3 ways that flows. Do you remember the 3 ways that heat flows?
What do you mean?
Well, it's not in your notes. We just talked about it verbally. No. But up is one of them. What is the one that goes, the heat rises? Nope. Starts with a C. It's condensation. No, not condensation. No. You want to play hangman with me? Okay.
OER?
E.
Well, there's a C.
And an O and an N.
O.
Conduction.
There's your C.
Conduction.
That's not the heat rising one. No, that's one form.
O.
Convection, right. So convection. And then there's one more, but it doesn't start with a C.
What does it start with?
What's the third kind? Get it from the sun.
A.
Radiation. There you go. Okay. So those are the 3 ways that heat moves: is conduction, convection, and radiation.
I like that.
Okay. So that is how heat flows. Now, when we're doing our lab tomorrow, we're going to be using this and essentially this too, because the convection currents within the water. But this is the main one where you're putting the metal sample into water. It's going to conduct through that water. Okay. So this is the main form of heat transfer that you're going to be working with tomorrow. Your heat is measured in either joules or calories. Okay, and here are some conversion factors that you can use within that.
Joules are what?
Calories, right here, calories. Right. Now, yeah, so the difference here is this is a little c and this is a big C. So this is a kilocalorie. Okay, they're the same thing. It's just they make it with a capital C. So if you look at the packages that your food comes in, so I have my little snack bar here for breakfast this morning. It's a capital C. So this means that this is 70,000. Well, because it's 70 calories with a big C. That means that it's 70,000 little c calories. With a little c, yeah.
That's so funny.
You just have to say it.
She'll freak out. Okay, so that's the difference. But you'll notice that all of your food, the calorie is always a capital C if they know what they're talking about. Okay, those have to be a double cup. There has to be 2 cups there, like one nested inside the other.
Chad, you look quite blue today.
Huh? There's more cups in the back on the bottom shelf of the moving thing. I think it's the second shelving unit in. All right. So some books use C for specific heat. A few of them use S. I've never really seen S, but C is most commonly what's seen. All right. So calorimetry is going to measure the heat that's transferred in a reaction. Calorimeter is essentially a device that stops the transfer of heat from the inside to the outside. So what he's getting out now is styrofoam cups. Okay, that's what we typically do calorimetry with here at the high school level. Okay, they have fancier calorimeters. Do we talk about that later on here?
Yeah, doesn't it look quite blue
No.
today?
Okay, so they have things called bomb calorimeters that they'll typically use like at the industrial level. And those are sealed more. They have more insulating. But these, just the styrofoam cups, give us pretty decent results. Okay? So calorimetry, we're going to measure the quantity of heat exchanged. And the first law of thermodynamics states that in an isolated system, heat can't be lost or gained. It's only transferred. So since the calorimeter is designed to isolate that, the heat lost by one thing, which yesterday the aluminum was losing the heat, and gained by the other, which was the water yesterday, is the heat that is exchanged there. So that's what you're looking at. Typical experiment then is to find the specific heat of an unknown metal by heating it to a known temperature. So if we put it in boiling water, we know the temperature is 100 degrees Celsius, okay? And then we put it in water of a known temperature, and the heat gained by that water then was lost by the metal. And so that's what you're doing tomorrow. You're going to do that with 3 different metals. You're going to do it with aluminum, brass, and copper. We don't do the unknown. What I do is I give you the accepted specific heat value, and you have to see how close you are to calculating that. Okay. So here's the formula that you'll be using. You know that this is our formula, and the heat lost by this equals the heat gained by this. So you can set this up in this formula here. Okay. So we have our metal mass, our specific heat of metal, which is what you're going to be solving for tomorrow. You have your change of temperature for your metal. So it goes from 100 degrees down to, maybe 28, 29 degrees. You have your water, and you have a negative value here because this is to balance this out, okay? So our water here, we've got our specific heat of water, which is given to you in your lab. It's given to you several times in this packet here too. And then you're going to tell what temperature the water, so if the water goes from 25 to 29, that would be its change of temperature. Okay. And then you can calculate this value from there. So each substance, for example, has a specific heat capacity. So for example, aluminum and lead, we've got aluminum here. If we had the same Q value given, we'd have the same mass of each one, but because aluminum has a higher number than lead, its temperature is going to change differently versus the lead.
That's cool.
Okay, so you can see the specific heat is higher, the change in temperature is lower, and vice versa. So when heating a system, results in the system having a greater energy because the energy is flowing into the system, while cooling a system results in the system having less energy as energy is leaving the system. You can see that with this heating curve. Okay, and then if we flipped it around, it would be your cooling curve. Specific heat capacity then is the measurement of the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. Molar heat capacity then is the amount that it would take to raise 1 mole of a substance. So you can, oftentimes you're provided with one or the other. You just have to kind of check your units on those. And then chemical systems change their energy through 3 main processes. We've got heating, cooling, we've got phase transitions, and chemical reactions. Okay. So then next time, this is going to be 15.5, which is next week.
Like all of the 400 mils are used.
That's fine. Anything bigger is fine too.
And bigger. You all use type of AP kits for those. I have 2 of them.
Did you check the cabinet right here?
Just one.
6. Cabinet 6.
No, that's good. That's you.
There may be some in the dishwasher too that can get.
No one that needs to do
Oh, I ate bacon yesterday.
Okay, so we've got, this is what one of those bomb calorimeters looks like, the more fancy type. Again, this is what they would use in industry. We just use styrofoam cups. Okay. So we've got almonds and cashews, and they want to know the energy for each nut and which provides more energy per gram. Okay.
I love almonds.
Never mind, I bet you it's cashews.
I love cashews too. They both have to be extra soft.
All right. So, they want to know the energy for each nut and which provides more per gram. So we've got our mass of our nut here, which is 6 grams. We have our specific heat of water, which is 4.18. And we have the change in temperature here. Wait a minute, this is not going to work out. Wait a minute. This is mass of nut. How much water do we have? Okay, so that's what we need to use is our water. Hold on. Let me erase this. I need to use my mass of my water because I'm using the specific heat of the water here. And we're also using the change in temperature of the water. So if I have 200 milliliters of water, how many grams of water do I have? Our 2,000 milliliters of water is how many grams? 2,000.
Good I did it right.
Because the density of water is 1 gram per milliliter. So if you have 1 gram of it, you got 1 milliliter. This is an equal ratio. Okay. Now we need to subtract this. So 40.5 minus 22.5 is 18. Okay, and now we're going to multiply this together. The heat gained by the water is the heat that was lost by the nut, right?
That's true.
So 2,000 times 18 times 4.18, that gives us 150,480, and that's going to be joules per gram. Let me see, my grams would have canceled. Yeah, that's just joules, right? Per yeah, per 6 grams. That's what it is, per 6 grams. Okay, so that's 6 grams of this nut, and it gave us that many joules. That makes sense? So if we want to take this down to joules per gram, what do I have to do? Divide by 6. So I'm going to divide by 6 here, and that's going to give me 25080, and that's going to be joules per gram. And that is for my almonds. Okay. All right, so let's do the same thing for our cashews now. This time, though, we only have 1,000 milliliters of water. We have 4.18 again for the specific heat of water, and then we need to figure out our change in temperature. 51.3 minus 22.5, and that's 28.8. So I ended up with 120,384, and that's going to be joules per gram. Or per, not per gram, per what? 5 grams, yep. Per 5 grams. So now I need to divide that by 5, and I get 24076.8 joules per gram. So which one's better? Almonds will give you more energy per gram. They don't have more water. They just had more water in the cup that the heat was transferring to that water. This isn't water in the almond. This is water here. Well, that we took that into account with our specific heat. All right. So you guys have some problems to do. You've got this one to do as a class together. You guys can work on these together as well. And then you have some other specific heat problems. All of these 15.4 and 15.4a in your packet are all due on Monday. Okay.
What is all due on Monday?
Everything up until 15.5.
Cool.
Okay, but that's till Monday. Okay, because tomorrow is a lab, Friday is Avonic, and then we're back to Monday again. Okay.
Sounds good. Let's move.
All right.
Can I have my test to do correct?